Hello, can you hear me?
Hello. Yeah.
Okay, so we'll continue with number theory. The question that I had given, I think a couple of questions at the end of last class. First one was show that a number in base 10, which is made by using just the digit 1. Basically, it can be something like 1, 1, so on, k times.
Yeah.
Is a perfect square, is a perfect square if and only if it has one digit. And only if it has one digit. Basically, any number of ones, like if you have more than one digit, then that cannot be a perfect square. That is what we have to show.
Yeah.
Did you try it out?
I thought we were doing the geometry class today. I mean, not geometry, AMC. So I did an AMC and not number theory questions.
Last class was number theory, Thursday.
Yeah.
Okay, maybe I forgot, but uh, okay, it's fine. We can do the AMC class next time. Okay.
Okay. Yeah.
So also in the AMC class, like I want you to focus on like whatever papers you do, focus
Mm-hmm.
on the problems from 15 to 25. Okay.
Okay.
Like actually the first 14 problems and all mostly will be easy, right?
Okay. Yeah.
Those are mostly anyway doable. The point is to improve on those last 10 problems.
Yes.
So whatever papers you attempt for AMC after today also, just focus on the last 15 to 25 and let's try to improve there. Okay.
Okay. Yeah.
Okay, so we'll try out this question. So obviously here we know that 1 is a perfect square, right?
Yeah.
We can see small numbers like 11 and 111, they are not perfect squares. But
Right.
we want to prove it in general that any number which has more than one digit and just ones will not be a perfect square, right?
Right.
So suppose we make such a number, let's say A has 1, 1, 1, 1, and so on, k digits, right?
Mm-hmm.
Where k is greater than equal to 2, right?
Yeah.
Then if you think about it, this can be written as such a number can always be written as A is equal to 1, 1, 1, 1, k minus 2 ones, and then a 0, 8 plus 3. Think about it. K minus 2 digits if you put, and then I put a 0 and a 8. Obviously, when you add 3 to it, it will become a 1, 1, right?
Yeah. Right.
This is the number representation, digit representation, or place value representation of this number.
Yeah.
So the point is, why have we written it like this? Notice that this works for any k greater than 2. Basically, 11 can be written as 0, 8 plus 3, and
Yeah.
111 can be written as 108 plus 3, right?
Right.
It works all the time, 1108 plus 3, right?
Yeah.
So the point is that when you write it like this, you should realize that the first number on the right side here, can you check its divisibility by 4? What is the divisibility rule for 4?
The last two digits must be divisible by 4.
Right. So here, obviously, it will be divisible, right?
Yeah.
So this number is going to be of the form 4k. It is divisible by 4, right?
Yeah.
So from here, we are getting that our big number A is always of the form 4k plus 3, right?
Yes.
Correct.
Yeah.
Now, If your big number is of the form 4k plus 3, then we have to check whether it's a square or not, right?
Right.
Now, if you remember in the last class, there was a question where we had to find the last digit of a square, right?
Right.
If you remember, there was a question, no, last, for example, the question was prove that the number which ends in 17 is not a perfect square, right? If you
Yes, yeah.
recall, there was a question like this, is not a perfect square.
Yes, yes.
And we saw there that if you take any perfect square, the last digit can be 1, can be 4, 5 or 6, or 9, right?
Right.
This is the last digit of a square. Why? Because we checked all the squares. So any number ending in 1, last digit will be 1, 2, last digit will be 4. Number ending in 3, it will be 9. Number ending in 4, it will be 6. 5, it will be 5. 6, it will be again 6 only, right?
Yeah.
Similarly, 7, it will be 9. 8, it will be 4. And that's it. 0, it will be 0, right?
Right.
Do you remember that question?
Yes.
So we saw that the last digit of a perfect square has to be these numbers, right? Correct?
Right. Yeah.
Now, similarly, we can also think of a number n and think of it mod 4. If you think of a number n mod 4, there are 4 cases that the numbers could be. It could be 4k, it could be 4k plus 1, it could be 4k plus 2, or it could be 4k plus 3, right?
Yeah.
If you think of a number mod 4, the remainders could be 0, 1, 2, 3, right?
Right.
And the squares, in each case, think about the squares. So if I do n square mod 4, right?
Mm-hmm.
When you do this, it will be still 0 mod 4, right? If n is 0 mod 4,
Yeah.
right? So when you do the square of this type of number, what will happen? It will be 16k square plus 1 plus 8k, right?
Right.
So this is divisible by 4, these two. Only it will be 1 mod 4 in that case, right?
Right.
Do you understand what I'm saying?
Yes, yes.
If it is this type of number, you can see that already 2 is a factor of this. So it will be 0 mod 4 after squaring, right?
Right.
Why? Because 2 comma 2k plus 1 and square it, it will become 4 into 4k plus 1 whole square. 4 into
Yes.
2k plus 1 whole square, right?
Yeah.
So again, it is becoming 0 mod 4 here. And finally, this type of number, if you do, it will be 16k square plus 2 into 4k into 3. So 24k plus 9. And you can see that these two are divisible by 4 and 9 is 1 mod 4, right?
Correct. Yeah.
So still it is coming 1 mod 4 only, right?
Right. Yes, yes.
So in any case, there are only 4 types of residue classes for a number given mod 4. Any number can only have 4 residue classes, these
Right.
4. And whenever you square them, you are always getting 0 mod 4 or 1 mod 4, right?
Correct.
So any square, any perfect square is always either of the form 4k or of the form 4k plus 1, right?
Yeah.
But our number in the previous page, you realize, was a number like this, right?
Right. Yes.
Which was 4k plus 3.
Yeah.
So it cannot be a perfect square.
Right. Yeah.
So what we have done here is analyzed that a perfect square is always of the form 4k or 4k plus 1, or it's always 0 mod 4 or 1 mod 4. But our
Yeah.
number here is 3 mod 4, right?
Yes.
So remember, this point is super important. This point. Any perfect square is always of the form 4k or 4k plus 1. It will be used in many problems. Okay.
Right. Yeah.
For example, now you can use this result to prove the following. So try it out. Prove that any number of the form 4 power n plus 2, 4 power n plus 3, 4n plus 3 power 2m plus 1, 5n plus 3 power 2m, 5 power 2, 5 power n plus 3 power 2m plus 1. All of these cannot be perfect squares. Use that condition to prove it. The condition on perfect squares modulo 4. The first two are direct, right?
Yeah, because they're not gonna be 0 mod 4.
Or 1 mod 4.
Yeah, or 1 mod 4.
Perfect squares have to be 0 mod 4 or 1 mod 4.
Right, yeah.
So those are directly 2 or 3 mod 4. You should just think about these three.
Yeah.
So if you think of 4n plus 3 power 2m plus 1, what you can see here is that obviously this is 0 mod 4, so we don't need to worry about it, right?
Yeah,
So
right.
this is congruent to 3 power 2m plus 1 mod 4, right?
Yes.
And then we have to just analyze this part. So is there any idea that you have to figure this out?
Mm, I was thinking like writing the powers of 3 sort of and making those. So like 3 to the
Like what?
power of 1, like 3 to the power 2m plus 1, 3 to the power of like 1 is like uh 3, 3 to the power of 2 is ends with 9, 3 to the power of
3
3
power
ends with
2, 3 to the power 2 you anyway don't have to take. It's 3 power odd numbers.
right. So then it starts on like a repeat, and then the odds are gonna be either 3, end with 3, or the odds are gonna end with 7.
But last digit doesn't matter for us. We are doing modulo 4, no?
Right, yeah.
It doesn't, we are not doing it by the method of last digit, right?
Right.
Because last digit of a perfect square could be many numbers, right?
Yes.
We are not doing it by that method. We are thinking of it modulo 4. So you don't have to try to find the cycle of last digits that you're trying to do right now. What you
Yeah.
should think of is, can we think of it as divided by 4? What will be the remainder of this, right?
Mm-hmm.
So what I would suggest is you can write this as 3 can be written as 4 minus 1, right?
Yeah.
And now you have to think of binomial theorem. You know binomial theorem?
I think you've touched on it a bit.
So basically x plus y to the power n, the expansion of this you need to know. And if you don't know it, you need to just revise it or study it a little bit. You can
Mm-hmm.
figure it out yourself. The point is simple. If you multiply it, it will become like this: x power n plus nc1 x power n minus 1 y plus nc2 x power n minus 2 y square and so on, right?
Yeah.
If you have not studied it, study it yourself. It's not very difficult. You can figure it out. And finally,
Okay.
NCN, last term is x power 0, y power n, right?
Yeah.
So know the pattern. The pattern is C. The first term starts off with the n power, right?
Mm-hmm.
And here power of y is 0, right?
Yeah.
Then the power of n is decreasing, n minus 1 for x, and y becomes 1.
Yes.
Then n minus 2, y square, n minus 3, y cube. Finally, at the end, it will be x power 0 and y power n, right?
Right.
So powers of x are decreasing one step at a time, and powers of y are increasing, right?
Right.
And these terms are binomial coefficients, NC1, NC2, NC3, NCn. They also come in Pascal's triangle. So if you study binomial theorem from anywhere, you will understand why these terms are coming. The reason is you are trying to multiply several of these, right?
Yeah.
Think about how you would make a term like, let's say, x square y, right?
Mm-hmm.
When you multiply these brackets n times, how would you make a term like x square y? Let's say there are three brackets, right?
Yeah.
If there are three brackets only and the power of n was 3, n is equal to 3. To make a x square y term out of these three brackets, let's remove the dots for now. Out of these three brackets, two of the brackets you have to select x, right? And the
Yeah.
remaining bracket you have to select y, right?
Correct.
So how many ways can you do that selection? Out of these three brackets, you have to select one y, right?
Yeah.
So 3c1 or equal to three ways, right?
Right.
You
Yeah.
could have selected one y from the third bracket or from the second bracket or from the first bracket. The remaining two will be x's.
Yeah.
Basically, what I'm saying is multiply x into x and multiply y from here. That gives 1 x square y. You will also
Yeah.
get a x square y if you do x into x from here and y from here, right?
Right.
So there will be three such x square y terms. Do you understand why there will be three such terms?
Yes.
So the point is, when it is n power and you want to make a term like this, right? What are you doing? You are selecting one y and n minus 1 x's from the n brackets, right?
Yeah.
But that one y can be selected out of the n brackets in any of the brackets could have been that y, right?
Yeah.
So there are n ways, right? No.
Correct.
N ways to select a y and remaining terms are all x's, right?
Yeah.
So this is known as n choose one, NC1. So many terms will come which will be like this, right?
Yeah.
The way to know what is the general value of NC1, NC2 and all, the formula is NCR is equal to n factorial by n minus r factorial by r factorial. This is the definition of NCR, and we are doing, these are the terms that are coming, right?
Yeah.
If you don't know all this, you need to study binomial theorem. Make sure it's important to know binomial theorem because in number theory, it will come as an application sometimes.
Okay.
Okay.
Yeah.
You can find it in any of the AOPS books. If you see AOPS volume 1 or volume 2, any of them, you will be getting binomial theorem somewhere. You just need to find it. Or the introduction to algebra book also somewhere towards the end, it will be there. Okay. So just find it and study it. It's important to know it. Okay.
Yeah.
So this is my theorem. And now what I have done is I have written 3 as 4 minus 1, right?
Yes.
So notice, according to this theorem, how I will expand it. It's very simple. You will just do the powers. The second term is minus 1. The first term is 4, right?
Right.
And the power is 2m plus 1, correct?
Correct.
So according to this theorem only, what should be my expansion? Let's do it. So first term would be 4 power 2m plus 1, right?
Yeah.
then it will be 2m plus 1 C1 4 power 2m and minus 1 power 1, right?
Yeah.
Do you see what I'm doing? I'm exactly writing the terms.
Yeah.
Then 2m plus 1 C2 4 power 2m minus 1 and minus 1 square, right?
Mm-hmm.
And like this, it will go on till the second last term, which will be the second last term just before this would have been nc n minus 1, x power 1, y power n minus 1, right?
Yeah.
So it will be 2m plus 1, and one term before it would be c2m, and it would be 4 power 1 and minus 1 power 2m, right?
Yeah.
And then the last term would be 2m plus 1 c 2m plus 1 4 power 0 and minus 1 power 2m plus 1, right?
Mm-hmm. Right.
Do you understand what I'm doing?
Yes.
I'm just writing the terms as 4 minus 1 power this. I'm expanding by binomial theorem, right?
Yeah.
And when you do that expansion, you can see that the powers of 4 are always there in all the terms till the second last term. See,
Right.
all these powers are there. 4 power 1 is there here, right?
Yeah.
So all of these first few terms are all divisible by 4, right?
Right.
Obviously, right?
Yeah.
There is a 4 everywhere. You can take a 4 common in the first, all of them terms, except the last term, right?
Yeah.
And the last term, if you see 2m plus 1, c 2m plus 1, anytime you have a ncn, that's value is 1. Okay, so this value is simply 1.
Yeah.
And 4 power 0 is 1, and minus 1 power odd number is minus 1, right?
Right.
So this last number is 1 into 1 into minus 1, right?
Yeah.
So basically, we can easily say that it is of the form 4k minus 1, right?
Yeah.
This whole number is of the form 4k minus 1, right?
Right.
And basically, that means it is minus 1 mod 4, right?
Yeah.
Or minus 1 mod 4 can be thought of as a 3 mod 4, right?
Yeah.
Do you understand what I'm saying?
Yes.
It is 3 mod 4 because it leaves remainder minus 1. So you can do multiply it by k minus 1 instead and say it is a remainder is plus 3, right?
Yes.
So we have shown that this number is of the form 4k plus 3 or 3 mod 4. So it cannot be a perfect square, right?
Right.
Is it clear?
Yeah.
Is there a doubt somewhere?
Mm,
Another way
no.
to do it would be
Mm-hmm.
you have, let's say, we do it in an alternative way.
Yeah.
Again, by using binomial theorem, but this time in a slightly different way. We can say 3 power 2m plus 1 can be
Mm-hmm.
written as 3 into 3 power 2m, right?
Yeah.
And 3 into 3 power 2m can be written as 3 into 9 power m, right?
Mm.
Why are you struggling with basic things like this?
Wait, 3 into what power n? Oh, right. Yeah, yeah. I thought you
We,
meant the 9 was in the exponent.
we can write 9 as 1 plus 8 to the power m
Yeah.
and expand by binomial theorem 1 plus 8. 1 plus 8 power m will be 1 power m plus mc1, 8
Mm-hmm.
power 1 plus mc2, 8 square, and so on
Yeah.
till mcm, 8 power m. The powers of
Right.
8 are rising, the powers of 1 are diminishing, but powers of 1 I'm not even writing because it always being 1.
Yeah.
And you can easily see here, all of these terms have at least divisibility by 8.
Yeah.
So obviously they are divisible by 4.
Right, yeah.
So the number here, this number is of the form 4k plus 1.
Mhm. Yes.
And what did we have? 3 times 4k plus 1, right?
Mhm. Right.
So we are getting 4k plus 3, right?
Yes.
And already it is 4k here. So overall number is clearly 3 mod 4.
Yeah.
Therefore, it cannot be a perfect square, this thing, right?
Correct.
Now you have to prove this one and this one.
Okay.
Use the same methods, nothing very different.
Yeah, so what I'm doing, I just made it like uh n 6 minus 1 n plus
You don't have to do
8
6 minus 1, that's annoying. You should do 1 plus 4, that's much easier,
1 plus 4.
right?
Oh,
That is so
yeah,
much easier, right?
right.
We already
So
know 3 power 2m, I have already shown you here, right?
yeah,
3 power 2m, we just now did 1 plus 8 and got it as 4k plus 1, right?
yeah, right.
So this number, second number is of the form 4k plus 1. And let's do
Yeah.
the first number and decide what it will be like.
It's also 4k plus 1.
Right. So that is obvious. So the overall number will be of the form 4k plus 2, right?
Correct. So not a perfect square.
Right. Because it is leaving remainder 2. It had to leave remainder 0 or 1, right?
Yeah.
And similarly, this thing will be 4k plus 3, right?
Yes.
Because we already know what this is, 4k plus 2.
Mm-hmm. Right.
Again, this is also not a perfect square, right?
Yes.
So simple applications of binomial theorem prove that all of these are not perfect squares.
Right.
That's why you need to use this theorem. That's why it is important. So just revise it after the class or find it from where you can read it. There'll be
Okay.
many easy tutorials available online. You can just read it.
Yeah.
Okay. Then, so far we have proved this question 111 k times is not a perfect square. What I want you to do is to generalize this statement. And how can we generalize it? So let's say we have a number NA, which is of the form AAA. This is being done K greater than equal to 2 digits, right? K times, right? And A could be anything from 1 to 9, right?
Yeah.
We have already proved the case that A is equal to 1. We have to still prove that it is cannot be a perfect square. But
Mm-hmm.
now in general for other digits also.
Yeah.
Okay, so uh, start with N2. Think of N2.
Mm,
So basically, you have 2, 2, 2 like this, right?
yeah.
What you should realize is N2 is obviously equal to 2 times 1, 1, 1, 1 and all, right?
Yeah, right.
And we already learned that 1, 1, 1 and all was of the form 4k plus 3, right?
Yes.
Right?
Yeah.
So 2 times of that would be of the form 8k plus 6, which is actually going to be 4k plus 2, right?
Yes, correct.
Modulo 4, this is 4k plus 2, right?
Yeah.
So that is clearly not a perfect square, right?
Yeah.
Great. So we have figured out N2 is not a perfect square.
Yeah.
Similarly, if you think of N6, right? It is 6, 6, 6, right? 6.
Right.
That is also even but not divisible by 4. For example, you can think of it as, or you can think of it just directly as 6 times this. So it is 6 times 4k plus 3, right?
Yeah.
So that is 24k plus 18, and that is technically 2 mod 3, 4 again,
Yeah.
right?
Yes.
So N2 and N6 are obvious from our original discussion of 1, 1, 1, 1, right?
Right.
Remember how we proved that it is 4k plus 3? What did we do?
We
We
did
wrote
the
it as 1, 1, 1, k minus 2 digits and
mhm.
a 0, 8 plus 3,
Yeah.
because that will still give 1, 1, 1, 1 only if you add it.
Correct.
And we said that obviously if it ends in 0, 8, it is divisible by 4.
Yeah.
Do you understand what I'm saying?
Yes.
So we are getting N2 and N6 are not going to work because they are of the form 4k plus 2, right?
Right.
What about N4?
And 4, um, that's like 4 times 1 so it'll be 12k plus 12, so it'll be a perfect square because it's 4k, it's just 4k then.
One second. But that is a thing to remember. One thing, just because a number is of the form 4k or 4k plus 1, does it mean it is a perfect square?
No.
Does not imply it is a perfect square, right?
Yeah.
Right now we have gotten that yes, it is 4k, but that doesn't mean it's a perfect square, right?
Yes.
It could be, right?
Yes.
Right? But now let's think about it a little more. We are thinking of N4, which is coming as 4k, right? N4 is
Yeah.
coming as 4k. And let's think whether it is a perfect square or not. So, in order to analyze this further, hmm, one second, let me think. Four times of this. What is N4 mod 4? Uh, it is 4 times N1, right? N1 was of the form 4k plus 3. So n4 mod 4 is clearly going to be divisible. Hmm. See, we saw earlier also that last digit of a perfect square could be what?
0,
Hmm.
1, 2, 4,
Wait,
5.
could it be 2? How can it be 2?
Oh, never mind, not 2. 4, 5, 6, 9.
Okay, so last digit could be 4 though, right? So that condition is also succeeding here, right? In n4.
Yeah.
Uh, last digit is working out. Okay, so n4 is actually 4 times n1, right?
Yeah.
And we know n1 is not a perfect square.
Right.
N1 is not a perfect square. So how can n4 be perfect square? It is 4 times something that is not a perfect square. 4 is a perfect square, right? So technically, if n1 was k square, we could have said it is 2k whole square, right? 4 times something that is not a perfect square. If you do the square, like it cannot be, no? Then uh, okay, let's pause on n4 for the moment. Let's do other ones. For example, n7 or n2. What about n2? N2 ends in 2, right? Right?
Yeah.
N2 ends in 2. It cannot be a perfect square because 2 is not in this list, right?
Yes.
N3 ends in 3 cannot be a perfect square for the same reason, right?
Yes.
Similarly, n7 and n8 also. So 4 of them cannot be perfect square because they don't have the correct last digit, right?
Right.
Also, it doesn't mean that if you have the correct last digit, you will be a perfect square, right?
Yeah.
We have eliminated n2, n3, n7, n8. We have also eliminated n6, right?
Yeah.
We don't know about n4 yet. N5 and n9. Let's think of n5 and n9. N5 is equal to 5555 k times. So that is 5 times of 4k plus 3. So that is basically 4k plus 15. So that is 15 is also 3 mod 4, right? N5 is of the form 4k plus 3, right? Correct?
Right.
So N5 cannot be a perfect square. We know that.
Yeah.
And N9 would be 9 times of 4k plus 3. So 9 into 3, 27. That is again 4k plus 3, right?
Yes.
Because N1 is 4k plus 3, and 9 and N5 are also 4k plus 3, right?
Right. Yeah.
So These two cannot be perfect squares, n5 and n9. The only case that is left is n4, right?
Yeah.
N4. It seems like it shouldn't be a perfect square, but we don't have a good proof of it yet. The reason I'm saying it shouldn't be a perfect square is because it's 4 times something that is not a perfect square. Uh, if n1 was a perfect square, right? And suppose it was m squared, then we could have said that 4m square is also a perfect square, 2m whole square. But n1 can never be written as m square, right?
Right.
So how can then 4 times of n1 become a perfect square? Like 4 times, but that is not a good proof. Maybe we have to do it in a different way. It is a number consisting of simply 4s, 4 times, and we have to figure out whether it's a perfect square or not. So it is clearly an even number and it is divisible by 4k, right? So
Yes.
if it has to be a perfect square, it will be the perfect square of an even number, right? 2m square, right?
Yeah.
If it is a perfect square, let's assume it is a perfect square, right? So it will be like this, no? It cannot be a perfect square of an odd number. That's impossible, right?
Yeah.
So you'll get 4m square should be equal to this, right? And now you're getting m square is equal to this, which is a contradiction. The only way it works is for m is equal to 1 or k is equal to 1, right? That's it.
Yeah.
Do you understand? That's the only case. If k
Yes.
is 1 and 4 is a perfect square. But if k is greater than 1, it doesn't work. Do you understand what I'm
Right.
saying?
Yes.
Because we are now saying that m square is 1111. We already proved that this is not possible except if k is 1.
Yeah.
So now what we have done is we have proven for any a can be anything from 1 to 9. It will not be a perfect square if k is greater than equal to 2, right?
Yeah.
Are you understanding what we have done so far in the class?
Yes.
Okay, then the next question is prove that there do not exist four consecutive integers each of which is a sum of two squares. Do you understand the question?
Yes.
Okay, so try it out. You have 5 minutes at least. You can take. I'll be back in 5 minutes. Okay, try it out.
Okay.
Are you getting something?
So like we know that any perfect square is going to be written in the form of 4k plus 1 or 4k plus 0. So if you add it says each integer is the sum of two squares. So wait, is it 4k plus 2? I thought it was 4k plus 1.
4k plus 1.
Yeah. So it says the sum of two squares. So the possibilities are going to be 4k plus 0 plus 4k plus 0, which will just be 4k. Then you have 4k plus 0 plus 4k plus 1, which is just 4k plus 1, and then 4k plus 2, obviously. So yeah, you have that. And then there's no option for like 4k minus 1 or 4k plus 3. So you can't have 4 consecutive integers that are the sum of two squares.
Basically, what we are getting is sum of two squares can always be of these forms, right?
Yeah.
And any four in consecutive integers, any
Yeah.
four consecutive integers have to be of the form. It will leave remainder 0, 1, 2, 3, mod 4.
Right. Yeah.
So they will be 4k, 4k plus 1, 4k plus 2, 4k plus 3. So
Yeah.
one of them will be 4k plus 3 guaranteed, right?
Yeah.
And if one of them is 4k plus 3, that can never be written as this plus 2 squares addition, right?
Yes.
Because the addition of two squares always will be one of these three, nothing else, right? So all
Yeah.
four of them cannot be written like this, correct?
Yes.
One of them will be wrong, so that's why it doesn't work. However, if you had a question where you want to have triples, three integers, each of which is a sum of two squares, then there are infinite possibilities.
Yeah.
Because triples will fit this, right?
Yes.
So actually for triples, you can construct many different triples. The point is that one example of a construction would be 4n power 4 plus 4n square, 4n power 4 plus 4n square plus 1, and 4n power 4 plus 4n square plus 2. These are clearly three consecutive integers.
Mm-hmm.
And you can write each of them as, this one is 2n square whole square plus 2n whole square, right?
Yeah.
This one is clearly 2n square plus 1 whole square plus 0 square, right?
Right.
And this one is 2n square plus 1 whole square plus 1 square, right? So
Yeah.
these three consecutive integers have been written as sum of two squares, right? So
Right.
you can keep taking different n's and you will get infinite number of such triples of integers, right?
Yeah.
Okay. Then the next thing is base representation. So when I say that, what I mean is how can I write a number in a different base? So let b greater than 1 be an integer. Any non-negative integer n,
Uh-huh.
any non-negative integer n can be uniquely written as, can be written uniquely as n is equal to sum of I goes from 0 to k, ai and b to the power I. Basically what that means is it can be written as ak b power k plus ak minus 1 b power k minus 1 and so on till a1b plus a0 for some integers, a0, a1, ak minus 1, ak, and these integers will always satisfy the condition that they are between 0 to b minus 1 with ak not equal to 0 if k is greater than 0. So think about it, it looks complicated, but basically what we are saying is we can represent any number in any base.
Yeah.
Here b is the base of those types of numbers. Usually what we do is b is 10 for us usually, right? When we write 2,
Yeah.
3, 4, we are writing it as 2 into 10 square plus 3 into 10 power 1 plus 4, right?
Yeah.
So notice that this is a 3-digit number and this one that we have written is a k plus 1 digit number, right?
Yeah.
K plus 1 digit number starts with a power of b power k, then it goes on to b power 1 and b power 0 here, right? Correct?
Right.
So
Yeah.
n can be written as here ak, ak minus 1 till a0. This is a number in base b,
Yeah.
right?
Mm-hmm.
Just like 2, 3, 4 here is written as 2, 3, 4 in base 10 actually, right?
Yeah.
So this base representation is super important, especially in certain types of problems where you have to change the bases, right? And
Yeah.
remember always that the digits that you're using will be between 0 to b minus 1, right?
Yeah.
We cannot use the digit b because the base was b, right?
Yes.
We cannot use a digit 10 when you use a base 10. We can only 0 to 9 is our digits, right?
Yeah.
Similarly, if you want to do base 2, you will have to use only digits 0 and 1, right?
Yeah.
Do you understand what is being done here, what I have said?
Yes. Yes.
So this is a general way to express any number in any base. And you have to remember the conditions that the digits will be between 0 to b minus 1. And the number here is a k plus 1 digit number in base b. Right?
Right.
Okay. So now using this definition, n is equal to summation a I b power I is equal to 0 to k. This definition of n as a base p number, one can realize from here is that ai, that is the ith digit of it, right? Or actually the I plus 1 digit, right? Because
Yeah.
this number is written like this ak minus 1, ai somewhere here, and then till a0, right?
Yes.
In base b. So a0 is the first digit, ai will be the I plus 1th digit,
Yes.
right? So if I
Yeah.
wanted to find a particular digit in this, you should realize that that will be equal to n by b power I minus n by minus b times n by b power I plus 1. And this here represents the floor function. Floor function basically means GIF, greatest integer less than equal to something. Greatest integer function. Have you seen this floor function before?
Yeah.
So basically, GIF of x, where x is 1.2 if you want, would be what?
Hmm.
1.
Yeah.
1.2 GIF is 1. If negative numbers, usually GIF is the number below it, right? So it would be minus 3.
Yeah.
And if it is an integer, GIF is same as this, right?
Yes.
So greatest integer function is a function that gives us the value of the integer that is less than or equal to the number inside the thing, right?
Yes.
So what I'm saying here and what you should try to figure out is that if you want any particular digit, right?
Hmm.
What can I do? I can do n divided by b power I, the base b power I. I need the I plus 1th digit.
Yes.
It is n divided by the base b power I, GIF, minus b times n divided by base b power I plus 1. So let's think about why that is so. So obviously we have to write n as this, right? So
Yes.
n was what? Ak b power k plus ak minus 1 b power k minus 1, and there will be ai b power I and so on till a1b and a0, right?
Yeah.
So let's calculate what is n by b power I, right? Correct?
Yeah.
So n by b power I, you have to realize that there will be a term ahead of b power I. That will be the term ai plus 1, b power I plus 1, right?
Yeah.
So here it would be ak b power k plus so on till ai plus 1, b power I plus 1 plus ai b power I plus ai minus 1, b power I minus 1, and then lower powers, right?
Yeah.
This is my n. Now, if I do n by b power I, what is that becoming? It is becoming ak b power k minus I, and so on till ai plus 1 b, right?
Yeah.
Plus ai, right?
Yes.
And after that, it will be divided by b, right?
Right.
After that, all the digits, there will be b in the denominator after that, right?
Right. Yeah.
And you should remember that we knew that all of these digits are less than b, right? For sure.
Yeah.
Because it is written in base b, right?
Yes.
So when you do fractions, it will be ai minus 1 by b and b square and so on. So when you do GIF here, floor function, all of these will vanish, right?
Yeah.
Because this is a full integer. These are integers, right?
Yeah.
Correct? Are you understanding what I'm saying?
Yes.
But the ones after that will become decimals, no? It will become fractions.
Right.
So when you do GIF of n by b power I, those will vanish, right?
Yeah.
Similarly, if I do n by b power I plus 1, you should realize that what will remain is everything ahead of it, right? Except a power I plus 1 will be the last one, right?
Yes.
Right? And
Yeah.
the terms will become a power k, b power k minus I minus 1, right? Because I have
Right.
divided by I plus 1 power now, right?
Yeah.
Do you understand? And a power I will come with a by b, right? Something like this.
Yes.
When you take GIF here, floor function, all of these will vanish.
Yes.
So you'll be left with this integer, right? Till here.
Yes. Right.
And then when I multiply that with b, notice that this will multiplying by b will make it match with this, right?
Yes.
And multiplying this by b will make it ai plus 1 into b, right?
Right.
So notice that multiplying this by b makes all of these match with all of these till here, right? See?
Yeah.
So now if you subtract these two quantities, what will be left? ai, right?
Correct.
Are you understanding what I'm saying?
Yes.
It is not very difficult. It looks difficult because we are using symbols.
Mm-hmm.
But this gives you a method to find out any digit of a base b integer, right?
Right.
Is it clear?
Yes.
So any particular digit of a base b integer can be found by this method. We have,
Mm-hmm.
if I need the I plus 1th digit or ai I need, then
Yeah.
I can do n by b power I GIF minus b times n by b power I plus 1.
Yeah.
You can try this on any base integer and find their required digits. Also, you should practice conversion of the bases. So
Okay. Yeah.
basically, if you have a number 2, 3, 4
Mm-hmm.
and convert it to base 8 and find out what it will be in base 8. Similarly, convert
Yeah.
it to base 2 and so on.
Mm-hmm. Yeah.
So those conversions are basically you can do it by division and keeping on taking remainders and all, right?
Okay.
So learn about these conversion of numbers from one base to another.
Yeah.
Base conversions. That
Mm-hmm.
is something easy only, and you should be able to figure out yourself what to do here.
Yeah.
So remember this general definition and this technique to find out a particular digit, and then try a few base conversions and all. We will see problems later on where it becomes useful to convert from one base to other. Okay.
Okay.
Okay. That's all for today's class. For the
Mhm.
next class, we'll do AMC problems. What you
Okay.
should focus on is any paper that you are trying out, just focus on the last 15 onwards.
Okay. Yeah.
So 15 to 25, those will be the more challenging ones. That is where you have to learn new stuff or improve your problem solving in order to make sure that you can do them.
Correct. Yeah.
Okay. So next class will be that, and we'll continue from this point then.
Okay. Bye. Thank you.
Bye.